Pretty ridiculous, right? I mean, how did Sasquatch get on the wing of the plane? But in all seriousness, this clip is from the 1963 Twilight Zone episode, A Nightmare at 20,000 Feet. In it, a man named Bob Wilson, portrayed by William Shatner, keeps on seeing a gremlin bent on destroying the wing of the plane he is currently traveling on. However, when he attempts to show fellow passengers the creature, it always mysteriously disappears. So that's the brief backstory to this episode, but that is not why we are here today. Our group is here because we were a little confused on how this gremlin is actually able to stay on the wing of the plane. I mean, even mankind's greatest hero Tom Cruise was barely able to hold on, and yet this demented Teletubby is able to do it with ease. So our group is going to find out what exactly is happening to this gremlin on the wing, and decide how strong it would need to be in order to stay there. So please, fasten your seatbelts, and prepare to enter the Fluid Mechanic Zone, which is a less popular spin-off of
The Twilight Zone.
First, our group decided to draw a free body diagram of the gremlin to see what forces are acting on it. Acting along the x-axis is the force of friction and the force of air particles colliding with the gremlin. Then, acting along the y-axis is the force of gravity and the normal force. Next, our group's prediction was that, in real life, this gremlin should have been blown off that plane. In order to prove that hypothesis, we concluded that if the force of air is greater than the force of friction, then the gremlin should be as good as gone. But if the force of friction is greater than the force of air, then the gremlin wins. Sound reasonable? If not, too bad. We're moving on. Thirdly, our group made some assumptions for this calculation. Since the video shows that the plane is traveling through a storm, we will be using a lubricated aluminum coefficient of static friction. We are using aluminum because, in our research, most planes are built out of that material. Also, there is no data for gremlins. Go figure, right? So, we are assuming that it has the same mass and surface area of an average person. Next, we will be assuming the plane will be traveling at a constant velocity of about 550 miles per hour. And luckily for us, the title of the episode told us the altitude the plane is traveling at. So, the air density at 20,000 feet is about 0.658 kilograms per meter cubed. Finally, the fun part, calculations. To find the force of the air, our group decided to use the Bernoulli equation to obtain the pressure that is acting on the gremlin. Next, we set our datum at the height of the gremlin and had our first point be at a small distance in front of the wing, and the second point level to the first, located on the gremlin itself. Also, we decided to measure and gauge pressure, therefore the pressure at point 1 is atmospheric, so it goes to 0. Then velocity 2 is 0 because it is the point of stagnation. Lastly, the z components cancel because they are at equal heights, leaving the equation to just the pressure head of point 2 and the velocity term of point 1. Solving for P2 and plugging in values, we found the pressure acting on the gremlin to be about 20 kilopascals. Then to find the force of the air, we took that pressure and multiplied it by the surface area of the gremlin to get 37.8 kilonewtons of force. That's going to be pretty tough to beat, I'm not going to lie. But nonetheless, our group shifted our focus to finding the friction. And to do that, we decided to balance the forces in the y direction. After doing that, we found that the normal force was equal to the weight of the gremlin. We plugged in the values of the gremlin's mass and gravity to calculate the normal force to be about 686.7 newtons. Finally, to get the force of friction, we multiplied the normal force by the coefficient of static friction to arrive at our final answer, which was 206 newtons, which is much less than the force of air. I mean, it's not even close. So bye-bye, Mr. Gremlin, and I hope you have a nice fall. Get it? Because he's falling from the sky and it's the fall semester? No? Oh well. But anyways, it just goes to show you that you can't believe everything you see in the movies, kids. However, you can't be hopeful in the fact that no matter how ridiculous the scenario is, Captain Kirk will always find a way to save the day. And for that, we thank you, Captain Kirk. And thank you, too, for watching our video. We hope you liked it. Also, if this is anyone other than Professor Ellsworth watching, please do not sue us for copyright violations, as we are just poor college students. But thanks again, and have a wonderful day.